Welcome to this problem walkthrough. In this session, we'll explore LeetCode problem number 2064, minimized maximum of products distributed to any store. This problem is all about optimizing the distribution of products among stores to minimize the maximum number of products any single store receives. We'll discuss the problem requirements, constraints, and approaches to solve it step by step. Let's dive in. To solve this problem, we need to distribute products to stores in a way that ensures the workload is balanced as evenly as possible. The objective is to minimize the maximum number of products assigned to any single store. This means that while some variation in the assignment may exist, we aim to keep the store with the highest product count as low as possible. Each product type can only be distributed to one store, but a store can handle multiple product types. For instance, if there are 5 product types, each type must be assigned to only one store, but one store can handle products from multiple types. The input consists of two main components, an integer n, which is the total number of stores, and an array quantities, where each element represents the number of products available for a specific product type. The output is a single integer representing the smallest possible maximum number of products that any store will hold. Let's consider the first example to understand the problem better. Here, we have 6 stores and 2 product types with quantities 11, 6. To achieve the goal of minimizing the maximum number of products per store, we can distribute the products as follows: assign 3 products of type 1 to store 1, 3 more of type 1 to store 2, and another 3 of type 1 to store 3. For the products of type 2, we will assign them across the remaining stores. So far, we have started distributing the products in a way that balances the workload evenly across the available stores. Continuing the distribution from the first example, we assign 2 products of type 2 to store 4, another 2 of type 2 to store 5, and the last 2 of type 2 to store 6. Now, each store holds no more than 3 products, which is the smallest possible maximum for this case. The key here is that by carefully splitting the products of each type across multiple stores, we successfully minimized the workload for the busiest store. The result for this example is 3, as no store has more than 3 products assigned. Now consider the next example, where we have 7 stores and 3 product types with quantities 15, 10, 10. To minimize the maximum number of products per store, we distribute the products as follows: we assign 5 products of type 1 to store 1, another 5 of type 1 to store 2, and the final 5 of type 1 to store 3. Similarly, we assign 5 products of type 2 to store 4 and another 5 of type 2 to store 5. Finally, we assign 5 products of type 3 to store 6 and another 5 of type 3 to store 7. This distribution ensures that no store holds more than 5 products, which is the minimized maximum for this example. In the last example, we have just one store and one product type with a quantity of 100,000. Since there is only one store, all products must be assigned to this single store. As a result, the maximum number of products assigned to any store is simply the total number of products, which is 100,000. This example highlights an edge case where no distribution is possible due to the limited number of stores. Additionally, the problem constraints ensure that n in quantities are within manageable limits, and we must consider scenarios such as having just one store, a large number of stores, or only one product type. These edge cases help us understand the boundaries of the problem and guide us in designing an efficient solution. To solve this problem, we need to distribute products among n stores in such a way that the maximum number of products assigned to any single store is minimized. One approach we could consider is the brute force method. The idea here is to test all possible ways of distributing the products across the stores. For each distribution, we would calculate the maximum number of products assigned to any store and keep track of the smallest maximum load we encounter. However, implementing this approach would require generating every possible combination of product assignments, which leads to an exponential time complexity. This makes it computationally infeasible, especially when the input size is large. Due to this impracticality, the brute force approach is not suitable for this problem. Another approach we could try is a greedy method. Here, the intuition is to distribute products one by one to the store that currently has the least load, dynamically balancing the distribution as we go. To implement this, we can use a min-heap or priority queue to keep track of the current load of each store. For each product type, we repeatedly assign its units to the least loaded store. This approach is more efficient than brute force, with a time complexity of O, m log n, where m is the total number of product units and n is the number of stores. However, this method focuses on local balancing and does not guarantee a globally optimal solution. The lack of optimality leads us to consider a third approach, binary search on the maximum load. The key idea here is to identify the smallest possible maximum load, x, such that all products can be distributed to the stores without exceeding this limit. We achieve this by defining a search range for x and verifying if a given x is feasible through a decision-making process. Specifically, for each product type, we calculate the number of stores needed to handle its units under the constraint x. If the total number of stores required is less than or equal to n, we search for smaller values of x. Otherwise, we increase x to find a feasible solution. This binary search approach combines efficiency and correctness, making it an attractive option for solving the problem. The chosen strategy for this problem is the binary search on the maximum load, as it balances efficiency with correctness. The key insight here is that minimizing the maximum load can be reframed as solving a decision problem repeatedly for different values of x. This allows us to use binary search to efficiently narrow down the smallest possible x. One critical observation that made this approach effective was realizing that the number of stores required for a given x can be calculated directly using the formula CL, quantities, I/x. This was the aha moment that simplified the feasibility check. Comparing the strategies, brute force guarantees correctness but is computationally prohibitive, while the greedy approach is faster but lacks optimality. The binary search method strikes the perfect balance, giving us an optimal solution with manageable complexity. By framing the problem as a decision-making process and leveraging binary search, we arrive at a solution that's both efficient and reliable for minimizing the maximum load across stores. The problem we aim to solve is to minimize the maximum number of products distributed to any single store. This means we want to ensure that the workload is as balanced as possible across all stores. With n stores and m products, each product must go to exactly one store, and we need to find the optimal way to distribute them. The naive approach, which involves trying all possible distributions, is computationally impractical, especially for large values of n and m. Instead, we use a binary search approach to make the solution efficient. The key idea in this approach is that if we can distribute the products such that the maximum load per store does not exceed a certain value x, we can also achieve this for any value greater than x. To define our search space, the minimum possible maximum load is 1, where products are perfectly balanced, and the maximum is m, where one store handles all products. We then perform binary search within this range to find the minimized maximum load. To implement this binary search strategy, we need a feasibility check to determine if a particular maximum load value can distribute all products without exceeding the store limit. For a given max load, we iterate through the stores and allocate products, ensuring no store exceeds this load. We calculate the number of stores required under this condition. If the number of required stores exceeds n, the max load value is deemed infeasible. The binary search algorithm begins by initializing the lower bound low to 1 and the upper bound high to m. While low is less than or equal to high, we compute the middle value mid and test its feasibility. If it is feasible, we lower the upper bound to mid 1, searching for a smaller maximum load. Otherwise, we raise the lower bound to mid plus 1, searching for a larger load. When the search concludes, the value of low will represent the minimized maximum load. This process leverages binary search to reduce the time complexity compared to a brute force approach. The feasibility check is critical to efficiently pruning our search space. By carefully verifying if a given max load can accommodate all products within the store limit, we ensure that the algorithm remains efficient. This approach is a significant optimization over brute force, which would involve enumerating all possible distributions, leading to exponential time complexity. Instead, binary search combined with the feasibility check offers a much faster solution. Regarding data structures, the algorithm relies on simple variables like low, high, and mid to manage the binary search process, as well as a counter to track the number of stores needed for a given max load. The time complexity of the algorithm is O, n asterisk log m, where log m comes from the binary search and n arises from the feasibility check. The space complexity is O(1), as the algorithm uses only a few variables. To summarize the approach, binary search is used to minimize the maximum load, and the feasibility function ensures that we can distribute products within the constraints efficiently. The pseudocode for this algorithm starts by defining the binary search function minimized_maximum with n stores and m products. Inside, the feasibility check function is _feasible calculates whether a given max load can distribute all products within the store limit. The main function initializes low to 1 and high to m, then enters a loop that runs while low is less than or equal to high. In each iteration, the midpoint mid of the current range is calculated. If mid is feasible, the upper bound high is adjusted to mid 1 to search for smaller maximum loads. Otherwise, the lower bound low is updated to mid +1 to search for larger maximum loads. The function exits the loop when the bounds converge, returning the minimized maximum load stored in low. For instance, consider an input where n equals 6 and m equals 11. Initially, the bounds are low equals 1 and high equals 11. In the first iteration, the midpoint is 6, and we check if this value is feasible. If it is, we adjust the bounds to continue searching for smaller feasible loads. In the second iteration of our example, the midpoint becomes 3, and we check if a maximum load of 3 is feasible. If it is, we update the bounds again to search for even smaller loads. In the third iteration, the midpoint is 2, and we test its feasibility. If a maximum load of 2 works, we adjust the bounds further. Finally, the loop exits when the bounds converge, and the minimized maximum load is found to be 2. This means that with n equals 6 stores and m equals 11 products, the optimal distribution ensures no store handles more than 2 products. This solution demonstrates how binary search allows us to efficiently hone in on the minimized maximum load, avoiding the computationally expensive process of enumerating all potential distributions. By leveraging the feasibility check and narrowing the search space iteratively, we achieve an optimal solution with significantly reduced complexity. This code solves the LeetCode problem number 2064, minimized maximum of products distributed to any store. The goal is to minimize the maximum number of products assigned to any single store while ensuring all products are distributed among n stores. The solution uses binary search on the possible values for the maximum products any store can receive. Here's a step-by-step explanation. 1. Helper function can distribute. This function checks if it's possible to distribute all products such that no store exceeds max_products. It iterates through the quantities list, calculating the number of stores needed for each product using ceiling division, quantity / max_products. If the total stores required exceed n, the distribution isn't feasible. 2. Binary search setup. The search range is initialized with left as 1, minimum possible maximum products per store, and right as the maximum value in quantities, worst case scenario where one store handles the largest product quantity. 3. Binary search execution. The algorithm repeatedly calculates the midpoint, mid, of the current range to test as a candidate for max_products. If can distribute, mid, returns true, it updates the result and narrows the search to smaller values, right equals mid 1. Otherwise, it increases the lower bound, left equals mid +1. 4. Result, the loop exits when the range is exhausted, and the smallest feasible value for max_products is returned. This approach runs efficiently in m*log, max_q, where m is the number of products and max_q is the largest value in quantities. Binary search minimizes the number of checks, and the helper function ensures the constraints are met for each candidate value. This guarantees the optimal solution. Here, we start with the Java implementation of the problem. First, we import the necessary utilities and define our solution class. Inside the class, we implement the method minimizedMaximum, which takes the number of stores n and an array quantities representing the product quantities. To solve this problem, we use a helper function called canDistribute. This function checks if it's feasible to distribute the products such that no store receives more than a given maximum number of products, max products. For each quantity in the array, we calculate the number of stores needed using ceiling division. This is efficiently done using the formula, quantity plus max products 1/max products. If the total stores needed exceeds the available stores n, we return false, indicating that the current maximum is not feasible. Otherwise, we return true. Next, we set up the bounds for a binary search. The lower bound is 1, and the upper bound is the maximum value in the quantities array, which we calculate using arrays.stream. We initialize result to the upper bound, as this will store the minimized maximum once found. The binary search begins, and while the left pointer is less than or equal to the right pointer, we calculate the midpoint as left plus right left /2. If canDistribute mid returns true, it means the current maximum is feasible, so we update result to mid. If the current maximum is feasible, we also adjust the search space by moving the right pointer to mid 1, attempting to find a smaller maximum. However, if canDistribute mid returns false, it means the current maximum is too small, so we move the left pointer to mid +1 to try larger values. The binary search continues until the left pointer exceeds the right pointer, ensuring that we examine all possible values within the range. Finally, when the loop concludes, we return result, which holds the minimized maximum number of products that can be distributed to any store while satisfying the constraints. This implementation efficiently determines the solution using binary search, ensuring optimal performance even for large input sizes. In this example, we are tasked with distributing products to 6 stores, aiming to minimize the maximum number of products in any one store. To achieve this, we use a binary search approach. We start by initializing the search range with left set to 1 and right set to the largest value in the quantities array, which is 11. The result variable is also initialized to 11, serving as the initial upper bound for the minimized maximum. In the first iteration, we calculate the midpoint, which is 6, and check if it's possible to distribute the products so that no store exceeds this number. Using the canDistribute helper function, we determine the number of stores required for each quantity. For 11 products, 2 stores are needed since 11 divided by 6 rounds up to 2. Similarly, 1 store is needed for 6 products, and 2 stores are required for 10 products, totaling 5 stores. Since this is within the allowed 6 stores, the midpoint value of 6 is valid. We then update the result to 6 and adjust our search range by setting right to mid 1, which is 5, to explore smaller possible values for the maximum products per store. In the next iteration, we update the midpoint to 3 by recalculating left plus right /2. We then check if it's feasible to distribute the products with a maximum of 3 products per store. For 11 products, 4 stores are required since 11 divided by 3 rounds up to 4. For 6 products, we need 2 stores, and for 10 products, 4 stores are required. This gives a total of 10 stores, which exceeds the available 6 stores. Therefore, a maximum of 3 products per store is not feasible. Consequently, we adjust the search range by setting left to mid +1, which is 4. Next, we calculate the new midpoint as 4 and repeat the process. This time, for a maximum of 4 products, 3 stores are required for 11 products, 2 for 6 products, and 3 for 10 products, totaling 8 stores. Again, this exceeds the limit of 6 stores, so 4 is also not a valid maximum. We then set left to mid +1, which is 5, narrowing the search range further. Now, the midpoint is recalculated as 5, and we check if distributing products with a maximum of 5 per store is feasible. For 11 products, 3 stores are required, since 11 divided by 5 rounds up to 3. For 6 products, 2 stores are required, and for 10 products, 2 stores are needed. This results in a total of 7 stores, which is still greater than the available 6 stores. Therefore, a maximum of 5 products is not feasible. We update the search range by setting left to mid +1, which is now 6. At this point, the binary search terminates because left is greater than right. The final result for this example is 6, meaning the minimized maximum number of products per store is 6. In the second example, the goal is to distribute products to 4 stores while minimizing the maximum number of products in any one store. We initialize the binary search with left set to 1 and right set to the maximum value in the quantities array, which is 8. The result variable is also initialized to 8. For the first iteration, we calculate the midpoint as 4 and check if it's feasible to distribute the products with a maximum of 4 per store. Using the canDistribute helper function, we determine that 2 stores are needed for 5 products, 2 stores are needed for 8 products, and 2 stores are needed for 6 products, resulting in a total of 6 stores. Since this exceeds the available 4 stores, a maximum of 4 products per store is not valid. We adjust the search range by setting left to mid plus 1, which is 5, and proceed to the next iteration. Next, we calculate the midpoint is 6 and check if a maximum of 6 products per store works. For 5 products, 1 store is required, since 5 divided by 6 rounds up to 1. For 8 products, 2 stores are needed, and for 6 products, 1 store is needed. This totals 4 stores, which is within the allowed limit. Therefore, a maximum of 6 products per store is feasible. We update the result to 6 and adjust the search range by setting right to mid 1, which is 5. In the third iteration, we calculate the midpoint is 5. Checking this value, we find that 1 store is required for 5 products, 2 stores are needed for 8 products, and 2 stores are needed for 6 products, resulting in a total of 5 stores. Since this exceeds the allowed 4 stores, 5 is not valid. We then set left to mid plus 1, which is 6. At this point, the binary search concludes as left is greater than right. The final result for this example is 6, meaning the minimized maximum number of products per store is 6. This approach ensures an optimal solution by efficiently narrowing down the search range while validating feasibility at each step. To analyze the time complexity of our solution, we begin with the binary search process. The binary search operates over the range from 1 to the maximum value in the quantities array. Since binary search repeatedly divides the range in half, the number of iterations required is logarithmic with respect to the maximum quantity value. This gives us a complexity of O log max quantities. Next, for each mid value considered during binary search, we need to verify if it's feasible to distribute the products while ensuring no store receives more than mid items. This verification involves iterating through the quantities array, calculating the number of stores required. The cost of this operation is proportional to the length of the quantities array, denoted as M, so it runs in O, M. Combining these two steps, the overall time complexity of the solution is O log max quantities *M, where the multiplication arises because the feasibility check is performed during each binary search iteration. Now, let's consider the space complexity of the solution. The binary search itself only requires a few primitive variables, such as left, right, mid, and result, to keep track of the search range and the current result. All of these are integers, contributing a constant O1 space. Additionally, the feasibility checking function, canDistribute, uses a single integer variable, stores_needed, to calculate the number of stores required for a given mid value. Since no additional data structures are created during the solution process, the overall space complexity is O1. This makes the approach highly space efficient as it does not depend on the size of the input. To better understand the efficiency of this approach, let's compare it with a brute force solution. A naive method would involve iterating over all possible values for the maximum number of products a store can receive, starting from 1 up to max quantities. For each possible value, we would check whether it's feasible to distribute the products, leading to a time complexity of O max quantities *M. By contrast, the optimized solution leverages binary search to narrow down the range of feasible maximum values. This reduces the number of feasibility checks from O max quantities to O log max quantities. As a result, the binary search-based solution is significantly faster, especially when the maximum quantity value is large. Let's break down the best, average, and worst-case scenarios for this solution. In the best case, the binary search converges quickly due to favorable midpoint values, leading to a time complexity of O log max quantities *M. The average case reflects the typical behavior of the algorithm, where binary search performs logarithmic iterations, and each iteration involves traversing the quantities array. This also results in a complexity of O log max quantities *M. Lastly, the worst-case scenario occurs when the binary search takes the maximum number of iterations, but even then, the complexity remains O log max quantities *M. This consistency across cases highlights the robustness of the algorithm under varying input conditions. Finally, let's mathematically justify the big O analysis. The binary search operates on a range determined by max quantities, requiring O log max quantities iterations to narrow down the range to a single value. During each iteration, the canDistribute function traverses the quantities array, which has a length of M, resulting in a cost of O m per iteration. When we combine these, the total complexity becomes O, log, max, quantities, *m, as the two operations are multiplicative. This calculation confirms that the optimized solution is highly efficient compared to a brute force approach, particularly when the range of possible maximum products is large. The logarithmic reduction in search space is what drives this significant improvement in performance. To start, one of the most common mistakes is misunderstanding the problem statement itself. It's crucial to recognize that the goal is to minimize the maximum load assigned to any store, not to minimize the total sum or average distribution. Misinterpreting this objective can lead to incorrect logic and invalid solutions. A helpful fix here is to carefully revisit the problem description and focus on minimizing the largest individual store load. Another frequent mistake is attempting to tackle the problem using a greedy approach, where products are assigned to stores one by one. While intuitive, this method cannot guarantee the minimized maximum condition and fails to find the optimal solution. Instead, this problem demands a binary search on the possible maximum load range, as it systematically narrows down the solution space. Finally, edge cases can trip up many solutions. Scenarios like having only one store, all products being identical, or having more stores than products often reveal overlooked logic or unchecked assumptions. To address this, testing with edge cases such as n equals 1 or products equals 1, 1, 1, 1 is essential for avoiding runtime errors and ensuring correctness across all inputs. Inefficient iteration during binary search is another pitfall to avoid. If your solution recalculates the load distribution by iterating through all products at every search step, the complexity balloons to O n squared * log, max, products, which can cause timeouts for larger inputs. Instead, you can optimize this by using techniques like prefix sums to calculate load distribution in O, n, per binary search step, significantly improving performance. Another subtle yet important detail is ensuring the correct calculation of the midpoint during binary search. Using low plus high /2 may seem fine at first glance, but in languages like Java or C++, it can lead to integer overflow for large values. The safer approach is to use low plus high low /2, which avoids overflow and ensures accurate midpoint calculations. From an interview perspective, this problem is an excellent demonstration of binary search on the answer space, a strategy often used in optimization problems. You should be prepared to explain why binary search is appropriate here and how it efficiently narrows the solution space. Emphasize your ability to analyze constraints and optimize performance, and be ready to discuss edge cases like n equals 1, n-lan, products, or scenarios with identical products. Interviewers may also ask follow-up questions, such as adapting the solution to handle weight-based products or uneven store capacities, so it's good to think ahead about how you'd adjust your approach in those cases. This problem shares similarities with several others that also involve binary search on the answer space. For instance, LeetCode 410, split array largest sum, involves minimizing the largest sum when dividing an array, which mirrors the idea of minimizing the maximum load here. Another related problem is LeetCode 1011, capacity to ship packages within D-days, where binary search is used to determine the minimum capacity needed to ship packages within a given timeframe. Similarly, LeetCode 875, Cocoa eating bananas, requires finding the minimum rate at which Cocoa can eat bananas to meet a time constraint. Finally, LeetCode 2187, minimum time to complete trips, employs a binary search approach to optimize the time needed to complete tasks. These problems are excellent practice for understanding how binary search can be applied to optimize and solve real-world constraints, making them highly relevant as you prepare for similar challenges. When considering alternative approaches, brute force is the most straightforward method. By iterating through all possible maximum loads and checking feasibility, you ensure correctness, but the computational cost is significant O, max, products, *n, making it impractical for larger inputs. On the other hand, binary search on the answer space provides a much more efficient solution. By testing the feasibility of different maximum load values, you can narrow down the range in O, n log, max, products. However, implementing binary search requires additional logic to verify feasibility, so it's not as simple as brute force. Another potential approach is dynamic programming, where you solve smaller subproblems of product distribution. While this can work for small constraints, it typically involves higher time and space complexity compared to binary search, making it less suitable for large inputs. Each method comes with its own trade-offs, and understanding these helps you choose the right strategy based on the problem's constraints and requirements. Great job making it through the walkthrough. To summarize, we tackled the problem using binary search, balancing efficiency and correctness to minimize the maximum products per store. Remember to apply this technique to similar optimization problems in the future. Thanks for watching, and be sure to like and subscribe for more content. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!